There we go. Okay, so induction is a very, very important proof technique. It's used all the time. I'm using it in the paper I'm writing right now. I mean, it's just a fundamental property of the positive integers or integers. So it's a fundamental property proof technique. It's really, especially if you're doing any sort of math related to computer science. I mean, it's all over the place. You can see it as an axiom. It's one of those. It's part of what are called piano axioms for the natural numbers and arithmetic. But let's not go there. So I'm going to state the principle of induction in its simplest form. And when you're going to see it, you're going to say, yeah, that's obvious. Okay. So then that's okay. That's fine. Okay. So here is the principle of induction. And I'm going to be stating this in various ways. But I want to start with the simplest formulation of it, which is not necessarily the easiest to use. Okay. So let S be a set, which is a subset of the positive integers, 1, 2, and so on. Okay. And suppose that it satisfies the following properties. So the first property that S satisfies is that it contains the number 1. Okay. And the second property, and this looks maybe a little strange, but what this property says is if a number is in S, then the next number is also in S. Okay, so for any positive integer, if n is in S, then n plus 1. So this set has the property that it contains 1. And there is this rule that says that if a number is in S, then the next number is in S. You can probably conclude what this set S has to be, right? So that's the principle of induction. It says that you must have every positive integer in S. Then S is equal to the entire set of positive integers, right? So 1 is there. And by the second property, if 1 is there, then 2 must be there. By the second property, if 2 is there, 3 is there, and so on and so forth, right? But basically what this says is that you're going to catch everybody. There are no numbers which are so far out that you will never catch them, okay? So that's the principle of induction, okay? So I'm sure you believe this, right? Or at least that's how you visualize or see the natural numbers, right? So we're going to catch them all this way. Okay, so now this is not the form which is which we use most commonly. So I'm going to rephrase this, okay, in a slightly different form. Okay, so here is another version, which is the same, right? It's the same thing. It's the same result or theorem or axiom or whatever. Same statement, I should say. No, it's not the same statement. It's the same concept, another version, just rephrased. Okay. Okay. So I have a property P, which might hold for some integers or not. Okay. That's here. Sorry. Okay. So we're given a property P, and suppose the following. Suppose that P of 1 is true. Okay, so P, the property holds for 1. Okay, and 2, if P of n is true, then P of n plus 1 is true. Okay, then the conclusion, what induction tells you, is that then for every n, P of n. Okay, so that's a different way of stating exactly the same thing, right? So the property here is in the first version that's being in the set S, right? Okay, but this is a very common formulation that we use in proofs. Okay, now the point of this is, I mean, the concept is simple. Okay, so the difficulty you might have is when we're going to use it. Okay, so the first examples I'm going to give you are like the classic, very standard examples of application of induction. And I think that the only tricky part is your intuition about variables. Okay, so let's start with like the simplest classic example, and yeah, so I can start here. So this is like this, I mean, everybody who teaches this will start with that example. Okay, so we're asked to show that if for any integer greater or equal to 1, if you add all the integers from 1 to n, this is the same as n times n plus 1 divided by 2. Okay, this is like the classic example. Okay, so I'm going to do this very slowly, explaining a lot of things. Okay, just to make sure that we're all on the same page. Okay, so I'm going to be using this previous formulation. Okay, so I'm going to define what the property I want is, and I'm going to show that it satisfies the two conditions 1 and 2, and then I'll be able to conclude that it is true for every possible n. Okay, so that's what I want. Okay, so let P of n be the following statement, which is exactly this: 1 plus 2 right up to n equals to n times n plus 1 over 2. So this is the property P of n. So this might be true or false depending on the number n. Okay? And I want to show that it is true for every n greater or equal to 1. So we want to show that P of n is true for all n greater or equal to 1. We use induction. Okay, so what do we show? So we're going to show two things. The first thing we're going to show is that P of 1 is true. That is usually the easy part. Okay, this is not the hard part usually. Okay, so we're going to show that P of 1 is true. And the second part, which is usually the harder part, if there is a hard part, is that if a P of n is true for a certain n, and this is where this, I mean, I'll get back to that when I get to that part, but so if P of n is true for some n, then P of n plus 1 is true. Arbitrary n, okay? But we're not assuming that P of n is true for all n. That is not what we're assuming. We're assuming it holds for some n. Some, we don't know what n is. We have this number n. The property is true for that n, and we show then the property must be true for the next number, n plus 1. Okay? If we prove these two things, 1 and 2, the principle of induction guarantees that P of n is true for all n. Okay? So hopefully up to this point, everything makes sense. Okay, if you have a question, just go for it right now before I jump into the proof. Okay, so far so good. All right, okay, so let's show. So I'm going to copy this here. Let's move here. This is what I want to show. Okay, so I want to show for all n, p of n, for all n greater or equal to 1. Okay, so to show p of n is true, that's what I want to show. Okay, so first of all, what about p of 1? Okay, what is p of 1? The left-hand side, we understand. Okay, there's some hand waving here on the left-hand side. We understand it's the sum of all numbers up to n. So if n is 1, it's just 1, right? So that's the left-hand side. What's the right-hand side? It's 1 times 1 plus 1 over 2, which is 1. This is true, nice and easy. Okay. All right. So 2. So now what do? I take some arbitrary, so let n be arbitrary such that p of n is true. Okay, so it is a number n for which this property is true. Okay, so we know that 1 plus blah, 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 right up to n is in fact equal to n times n plus 1 over 2. Okay, so at this point, if you're going, wait, isn't that what we want to prove? Okay, yes and no. We want to prove that this is true for all possible numbers n. What I'm assuming here is I choose some n. I don't say which, but I'm choosing an n for which this is true. I'm not saying this is true for all possible n, but for some n, it is true. And I want to conclude that it's going to be true, this property for the next number. Okay, so hopefully this is very clear. Okay, and this, you always keep this in mind. The problem, I think, comes from, and it's not only in high school. I mean, it's all over in maybe it, I don't know, but we write an identity and we don't quantify them. So when you see this 1 plus 2 right up to n equals n times n plus 1 over 2, we see this as an identity, right? But it's just an equality, which might be true for some n, for all n, for no n. Okay, so it's the quantification which is really important. Okay, so don't see this as some identity which is always true, because that's what we're trying to prove. Okay, all right, so this n, this special n, satisfies this property. What do I want to show? I want to show that p of n plus 1 is true. So this is the second part where there might be some technical difficulties here. Okay, but these are sort of easy to fix or to understand if you practice them a little bit and somebody actually tells you that there is a difficulty. Okay, so what is p of n plus 1? I know what p of n is. Okay, now in this particular example, it's slightly unfortunate, but the left-hand side is a bit hand wavy. You have to understand that what's written on the left-hand side is what? It is the sum of all integers from 1 to n. That's what's on the left-hand side. So for p of n plus 1, what will be the left-hand side? It will be the sum of all integers from 1 to n plus 1. Okay, so what is p of n plus 1? Let's write it. It's 1 plus 2 right up to n plus 1. That's the left-hand side. What is the right-hand side? Okay, there are two ways you can see this, and you could have done this also on the left-hand side, but the right-hand side is n for p of n. It is n times n plus 1 over 2. Method 1, you replace n by n plus 1 in this expression. You will get what you want. Okay. Method 2, what I'm seeing here, p of n says if I add all numbers from 1 to n, the result will be that number n times the next one divided by 2. Okay. So p of n plus 1 should be, if I add all numbers from 1 to n plus 1, the result should be that number, n plus 1, times the next, n plus 2, divided by 2. Okay, so this is p of n plus 1, which I'm trying to show is true, provided p of n is assumed to be true. Okay. All right, so this is what we call the induction hypothesis. Okay, so I'm making a hypothesis on n, which is that P of n is true. The property holds for this n. I know I'm repeating a lot of stuff, but okay, that's my job. Okay, so if you're finding this totally trivial and obvious, and sorry, enjoy it while you can. Okay, so this is the induction hypothesis. If when you're doing a proof by induction, you do not use the induction hypothesis, there is probably a big problem with your proof. Okay, so beware of that. So you have to use this at some point. If not, either your proof is completely wrong, or you've managed to find a direct proof which does not use induction, and then you shouldn't be phrasing it as a proof by induction. Okay. All right. So for example, this identity, there is a proof that doesn't use induction, which is actually maybe nicer. Some people say that proofs by induction are not the most elegant, but sometimes there's no way out. Okay. But it's a good tool, an important tool, a fundamental tool to have in your toolbox. Okay, so enough talking. Okay, so I want to prove this. So I'm going to start with the left-hand side, which is the sum of all numbers from 1 to n plus 1. And I want to get to the right-hand side. I want to use my induction hypothesis. Okay, so what does it tell me? It says that the sum of numbers from 1 to n is that nice little expression, n times n plus 1 over 2. So how can I use it? Well, you see that if you look at all the numbers over here, right, this is the sum of all the numbers from 1 to n plus n plus 1. Okay, so now I can apply my induction hypothesis. Right, the induction hypothesis says that this is equal to n times n plus 1 over 2. Okay, so the sum from 1 to n plus 1 is equal to, and I'm using my induction hypothesis, it is equal to n times n plus 1 over 2 plus n plus 1. What do I want to get is this awfully written thing here that I'm going to fix. It's n plus 1 times n plus 2 over 2. Now, what's left to do here, you can probably guess that if you put this on a common denominator, things should go well. So let's see, this is n times n plus 1 plus 2 times n plus 1 over 2. And if you factor out the n plus 1, you'll be left with n plus 2. And we're done. Right? So I've proved that if I have a number n for which P of n is true, then P of n plus 1 is true, right? And I've proved that P of 1 is true, so P of n must be true for all n. Any questions at this point? What I'm going to be doing, where did the 2 for the n plus 1 come from? This one? Common denominator? Yeah, good. Okay. So I just put everything on 2. So I had to multiply my n plus 1 by 2. Okay. Then I factored out the n plus 1. Okay. So I'm going to be doing more examples. Then I'm going to be tweaking my induction, principle of induction to make it a bit more general, a bit more useful, you'll see. But it's not a big change. And I'm going to keep it short today. That's all I'm going to do. The harder examples I'll keep for next time. Okay, so today I'm just going to be doing some fairly straightforward, pretty straightforward examples. Okay, so let's do a second example.
Sir?
Yep.
Real quick, I'm not sure I understand why like the sum of 1 plus 2, well, all numbers before n, and like with like the black scribble under it, like on the side, is equal to the same thing but with n after, and then you still keep the n plus 1?
Okay, so yeah, okay. So what's written here, what is that? It's 1 plus 2 plus 3, right, up to n plus 1. I have to go through n, right?
Yeah.
So I mean, if I take the sum of numbers from 1 to n plus 1, it's the sum of numbers from 1 to n plus n plus 1. I'm not saying anything deep here.
Okay, yeah, I get it.
See?
Okay.
Yeah, okay.
Yeah, great, thanks.
Yeah. Okay. All right, second example. So let's prove that n. Now, I'm not saying that these can only be proved by induction. There are some, and I'm going to show you an example where it's a one-liner without induction, but I want to illustrate induction. So prove that n is less than 2 power n for all positive integers n. Okay. All right. So I'm going to use induction. The best thing you can do, I really, it's just being really super organized really helps. If write exactly precisely what P of n is really, and just work with that. That's gonna help you, I think. So what is the statement that I'm trying to prove for all n? It is that n is less than 2 power n. That's the statement, okay? And I want to show P of n is true for all n greater or equal to 1, right? That's what I want to show. We're gonna see examples where we're gonna write down a statement like this, which is true, but not for all n. I mean, it'll be true for some n, but not all. So, but here it turns out that it's true for all n greater or equal to 1. So induction tells me how do I do it? Show it for 1, and then when you take an n that works, it also works for n. Show that it also works for n plus 1. Okay. So first, I'm going to show that P of 1 is true. Let's see. If n is 1, I want to show that 1 is less than 2. Yeah, that's easy. So in 97.3% of the time, the induction basis, which is what we call this part, is easy. It's not always true. There are some weird examples where the basis is the tough one. I don't have examples in mind, but it happens. Or is tough by itself. That could be hard. Okay. Okay. Next step, I want to show. So suppose that n is such that P of n is true. Show P of n plus 1 is true. Okay. So we suppose, that's our induction hypothesis, we suppose that n is less than 2 power n. Again, erase from your mind that this is an identity. It is a statement about the number n, which is a specific number. Okay, this is really important. And I want to show P of n plus 1. So what is P of n plus 1? It is that statement for n plus 1. So that's pretty straightforward here. I have to show that n plus 1 is less than 2 to the power n plus 1. Okay, knowing that n is less than 2 power n, induction hypothesis. Okay, all right, so let's see. Well, I've got n plus 1. I want to show that it is less than something. Well, a good start is just to apply the induction. So I know where this is going, but this is what I would do even if I didn't know where I was going. Okay, I would try that. It might not always work. That's the problem, but let's see. If the people asking the question are nice people, then this should work out. Okay, but there might be some work involved in getting to what we want to get. Okay, so n plus 1 is less than what? I'm going to apply the induction hypothesis here immediately, right? N is less than 2 power n, right? So this must be less than 2 power n plus 1. Careful, the plus 1 is not in the exponent. N is less than 2 power n, 1 is less than 1, so the sum must be less than the sum. Hopefully everybody sees what I did. Okay, I applied the induction hypothesis on the n, but this on the right, I don't have the right expression. I have 2 power n plus 1. What I want is 2 to the power n plus 1. Now, if I'm lucky, this will be true. I'm just going to put that like that because I don't know yet if that's true. If it is, I win, right? If I can prove this is true, then I win. So why would this be true? 2 power n, I add 1. Would that always be less or equal to 2 to the power n plus 1? Okay, well, what is that? This is my scrap paper. This is 2 times 2 power n, right? 2 to the power n plus 1 is 2 to the power n times 2 power 1, which is twice 2 power n. Hopefully everybody's okay with that. What is that? That's 2 power n plus 2 power n. Do I have believers? So is it true then that 2 to the power n plus 1 is less or equal to what I want? Do you see?
Don't you mean greater than 2n plus 1?
I want this to be less than this.
Oh, all right.
Yeah, it's just the way I'm saying it. It's just, yeah.
Right.
But everybody sees why this, I mean, believes, you see it's true.
Yeah.
Yeah. Yes, no, yes, maybe, yes.
Yeah.
I got one.
Yes.
Okay, yeah, because 1 is less or equal to 2 power n. So we're good, right? So yes, we're good. Okay, so that was my scrap paper. I'm going to write it properly now. Okay, this is scrap paper. Okay, you don't want to write it like that. Okay, so I'm going to rewrite this. N plus 1 less than 2 power n plus 1. This is by induction hypothesis, right? This is less or equal to 2 power n plus 2 power n, since this is true for any n, right? And this is 2 times 2 power n, which is 2 to the power n plus 1. Nice and clean, well written. Okay, but I wanted you to see how I sort of worked it out. Okay. Okay, now, admittedly, you guys are not used to playing with inequalities very much. But that one is not so bad. Let's put it that way. Okay, this is really just pretty elementary. Okay, even though it might be relatively new. Okay, or unusual. Okay, but you see, we were fortunate in that by applying the induction hypothesis, I got something which wasn't too big already, 2 to the power n plus 1, and I could then show that this was less or equal to 2 to the n plus 1. And so I was all good. Okay. All right. Questions on this? Okay, let's move on to example 3, which is completely different. I mean, the shape of the thing is the same, but the technicalities in using the induction hypothesis and so on and so forth, this could vary quite a bit from problem to problem. Okay, we're asked to prove that 3 divides n cubed minus n for every integer, n is an integer here, greater or equal to 1. Okay. Does anybody see a short proof without induction? I'm curious. Very short. Using a sledgehammer. Okay. Hint. 3 divides n cubed minus n is the same as saying that n cubed is congruent to n mod 3. Let me write this here. This is equivalent to, let's not use that. Let's use that. This is equivalent to saying that n cubed is congruent to n mod 3. Yeah, why is this true? Do you know? Some old dead guy already figured it out long time ago. Fermat. So if you look at Fermat's little theorem, the second part, it says this is true, right? Which is true by Fermat's little theorem, part 2. Okay, I just wanted to mention that is a possibility. Okay. Now, I'm not a huge fan of asking in tests, use such method to prove something. Usually I just like, if you can prove it, you can prove it. That's good. However, for induction, I might very well ask you to prove something using induction because I want to see that you're able to. By the way, it's not on the next test, right? But so even though you would see this immediately, that would be fine, that would be great, but I would still want you to prove it by induction, okay, which is what I want to do here. Okay, so this is a direct proof. Okay, but here's now a proof by induction. Okay, so what is the statement P of n? Now you see it's a bit different from the other ones. It's not an identity, it's a statement. So P of n is the statement 3 divides n cubed minus n. This is the statement, and I want to show that this is true for all n greater or equal. So to show P of n is true for all n greater or equal to 1. Okay? So if I'm using induction, that means that I'm going to show 2 things. The first thing is I'm going to show that P of 1 is true. 3 divides 0. Yes, everything divides 0. This is obvious. Right. Second thing I need to show is if I take an n for which this is true, then it will also be true for n plus 1. So if, and let me write it like that. I really want to write it out because I know, I mean, I know, I still remember seeing this in CJEP and having sort of I mean, it wasn't like totally clear. I could do it technically, I could just prove it, but it wasn't like crystal clear what I was doing. So you get good marks, but you're just like, you feel like, I'm not sure exactly what I can do it, but I don't feel like I'm really handling it right. But this is important because it's not that hard. It's really just a question of getting in the right frame of mind. And once you go into that right frame of mind, it's just like, boom, just like exponential growth. Okay, so if n is an integer such that P of n is true, prove P of n plus 1 is true. Okay, so our induction hypothesis is this, is that 3 divides n cubed minus 3. So n is a number that does this, that has this property, and I need to prove that 3 divides, so what is p of n plus 1? It is 3 divides n plus 1 cubed minus n plus 1, right? That's the statement for n plus 1, okay? All right. So here we go. So I want to prove 3 divides this, knowing, so the hint is that 3 divides n cubed minus n. So what do I do with this? If you look at it a little bit, you say, well, let's expand the cube and see what happens. Okay, so I'm going to take a look at n plus 1 cubed minus n plus 1. If I want n cubed minus n to play a role somewhere, I'll have to expand this cube. I have no choice. So what is that? I'm going to expand the cube. This is n cubed plus 3n squared plus 3n plus 1. If you're going, whoa, is it cheating? No, I know how to expand the cube really quickly. And in fact, I can expand any power I want very, very quickly. And you will know this in a couple of weeks. And this is something that every high school student should see, but they don't. It's like super easy, super cool, super useful. But anyway, I'm not master of the universe, so I can't make that happen. Okay, so this is this, right? Okay, I've expanded the cube. If otherwise you just multiply it out, right? Until in the next couple of weeks when you'll know how to do it quick, or if you already know it, that's great. Okay, so I want to get n cubed minus 3 involved. So there is an n cubed minus 3 here. So let's see, this is n cubed minus 3, sorry, minus n. So I've got the minus n here, right? So this is an n cubed minus n plus 3n squared plus 3n, and then 1 minus 1 are gone. Okay, so hopefully everybody sees that these are the same. Okay, and hopefully many of you see that we're done, because 3 divides this by induction hypothesis, and clearly 3 divides this because it's 3 times n squared plus n, and so we're done. Okay, so let's write this. Okay, so let's write it this way. So this is equal to 3k plus 3 times n squared plus n for some k by induction hypothesis. Right? Okay, so n cubed minus n is a multiple of 3. And so this is a multiple of 3. This is 3 times k plus n squared plus n. So we're done. Did I go too fast at the end there? Was that too...
No, it's fine.
That's good? Okay.
Yep.
So I split it up into 2 parts, and I got one part. I got one part, which is induction hypothesis. The other part, clearly multiple of 3. So we're done. Okay. All right.
Sure.
Yep.
Is the 3k there only to show that 3 divides n cubed minus n?
Yeah. I wrote it like that because it was easier. I could have written, well, n cubed minus n is a multiple of 3. 3n squared plus 3n is a multiple of 3. So the sum is a multiple of 3. I could have written it like that, but I just wrote, yeah. Okay, so here's my next example. I don't know if did I number them? Yes, I did. Such
Yeah,
a
this
nice-
one's 4.
Yep. So show that 2 to the power n is strictly less than n factorial for all n. Now you might be expecting greater or equal to 1, but that wouldn't be true, but it is true for all n greater or equal to 4. Okay. Now, if this looks like a job for induction, except the version we have doesn't work if we start at 4, which is very annoying, right? Because actually this is really not very difficult using induction, but the version we have starts at 1. But if you think about it, we should be able to start anywhere we want, because all it says, so look at what it says. You start at 1, and if 1 is there, then 2 is there. If 2 is there, 3 is there, 3 is there, so and so on, and just you get everybody. But suppose I start at 4. Suppose I have a set that contains 4, and I know that whenever a number is in that set, then the next one is in that set. Then I can conclude intuitively it should be true that every number starting from 4 and up will be there, right? And that's true. So to use induction here, I need to tweak my original theorem, axiom, original statement. Okay, so here is my principle of induction tweaked. Okay, so rather than start at 1, I'm going to start at whatever. Okay, so let B, and to really make it as, because, okay, I'm going to try to convince you that this is no more general than what we had. It's basically the same statement. Okay, so I can start at any integer, even if it's a negative, and that can be very useful. So let B be, let B be an integer. Okay, suppose that property P satisfies the following. One, P of B is true. Okay, as expected, that's where I want to start. 2, if P of n, yeah, no, wait. Let n greater or equal to B such that P of n is true, then P of n plus 1 is true. Okay, so whenever P of n is true for n at least B, then P of n plus 1 is true. Conclusion is that P of n is true for all integers at least B. So this is my more general version of induction. But it's not more general in any, it's more convenient because now we can start anywhere we want. Now, why would this be true if the other one is true? Think about it. All the statement of induction says it's about a sequence of integers starting at 1 point. So if you start at -5 and you want to show that you have everything -5, -4, -3, all of them up, just shift it up to 1, use the usual induction, and then shift back. I mean, it's just, okay, so why is this true? It's just, it is just, so this is very intuitive, but I could write it down, but I don't want to get bogged down into the details. It is just regular induction shifted That's all it is. Do you see what I mean? Does that make sense?
Yeah.
Yeah.
I'm just wondering why you added the condition in part 2 that n is greater than b.
Yeah.
Because we already sort of know that if p of n is true.
I could have written no. You need to be. You need n equals to b in there, because you want to start at b, go to b plus 1,
Okay.
and then from b plus. Because if this would be very tricky if you in part 2, if n is bigger than b, you're not. I mean, and this is really subtle. Yeah. Do you see what I'm trying to say with great difficulty? So
Really?
yeah, so it's true for B,
Mm.
and the second part you really need to start at B, in the sense that if it's true for B, it's true for B plus 1. If it's true for B plus 1, it's true for B plus 2, and so on. If in the second part I started with only n strictly bigger than B, I couldn't conclude anything,
Right.
right? So I really need to start at B. But that's a subtle question. Yeah, but I mean, we'll be playing with this enough that everything will be clear. Okay, so let's go back to our question now, which is this. This, like that. Yeah. Damn. Yeah. Okay, so let's do that. Okay, so I'm going to use this new, this slightly tweaked version. So we use this new improved version of induction. Okay, so my statement P of n is 2 power n less than n factorial, and I want to show that P of n is true for all n greater or equal to 4. Okay. So I start at 4. So 1. P of 4. What is P of 4? 2 power 4. Is that less than 4 factorial? Yes. 16 is less than 24. Nice and easy. Okay. Second, let n be at least 4 such that P of n is true. To prove P of n plus 1 is true. Okay. So let's write this up. So my induction hypothesis is that n satisfies this 2 power n less than n factorial. Okay, and I want to prove that P of n plus 1 is true. So what is P of n plus 1? You just replace n by n plus 1. So this is 2 to the power n plus 1 less than n plus 1 factorial. Okay, so this is what I want. Okay, this one is similar to the previous one. Okay, we have to play with these inequalities. So let's start with 2 to the n plus 1. I'd like to get 2 power n involved, obviously. So let's write this. This is 2 times 2 power n, right? So by induction hypothesis, this is less than 2 times n factorial, right? I've replaced this. Okay. If I am fortunate, this will be less than n plus 1 factorial. We hope it is. So that's my scrap paper here that I need. So this is my, I don't know, is this less or equal to n plus 1 factorial? I don't know. Okay, well, 2 times n factorial, is that less or equal to n plus 1 factorial? How do I compare these two things? Well, wait, let's see. Oh, I'm gonna keep the blue stuff. Okay, n plus 1 factorial is n times, no, it's not. It's n factorial times n plus 1, right? And I want n factorial times 2, hopefully, to be less than n factorial times n plus 1. So all I need is for 2 to be less or equal to n plus 1. Is that true? Yes. N is at least 4, so it is n plus 1 is certainly at least 2. Yes. Hopefully you see how my approach to this is. Okay, of course I mean I still knew where to go, but okay, so let me write this properly. Okay, so I've got 2 to the n plus 1, which is 2 times 2 power n. This is less than 2 times n factorial by induction hypothesis, right? Now, 2 is less or equal to n plus 1. Because n greater or equal to 4 means that n plus 1 is at least 5, which is at least 2, right? We have a lot of wiggle room, okay? So 2 to the n plus 1 is less than n plus 1 times n factorial, which is the same as n plus 1 factorial. Is that okay?
Yep.
Yeah. Okay. Now, don't confuse we're playing with inequalities here. This has nothing to do with induction, right? This proof strategy is induction, and I had to mess around depending on the problem on inequalities or some algebra or whatever. So it depends on the question, right? Here is a couple more, and then I'll be done. Where are you? What are you? Yes. Okay, here we go. Example 5, I guess.
Yeah, it'd be 5.
Yes. Okay, example 5. Show that for every n greater or equal to 0, if you add all the powers of 2 up to the nth power, this is the same as 2 to the power n plus 1 minus 1. There are tons of alternative proofs of this. This is a well-known fact, a very useful fact, but we're going to prove it by induction. Now notice that we start at 0 here, so my original principle of induction did not quite fit, but now I have a version that allows me to start wherever I want. Okay, so proof by induction.
But since we start with 1 plus and we end with -1, could we just start at 2 to the 1 plus 2 to the 2 and equals 2 added to
Yeah.
the n plus 1?
You could tweak yeah, here's another way you could do it, by the way. You could say, okay, let's just prove it for n equals to 0. It's done. and then prove the rest by induction. That's another way. Or you could try to reformulate it to start at n equals to 1. Yeah.
All right, thank you.
But you have to be, I mean, the way what you were saying, I'm not sure it actually, you still have to plug in n equals to 0 in there, but you might be able to reformulate it, yes, to start at 1. That's another possibility, obviously. But in any case, now we have a version that allows us to start anywhere we want, so it's fine. But either way, yeah. Yeah, but actually your comment is interesting, because in my next example, we'll have some choice on how we're going to write down the statement we want to prove, and they might not all be the same. So we'll get back to that. Okay, so if I'm going to prove this by induction, I need to state what P of n is. So P of n will be sum of all the powers of 2 up to the nth power is equal to the nth plus 1th power of 2 minus 1. That's what I want to show. I want to prove P of n is true for all n starting at 0. Okay, so I will prove it for 0. So what is this statement for 0? So again, there is sort of hand waving here on the left-hand side. The way it's written seems to imply that n is at least 1, but it's understood that we take the sum of all powers of 2 starting at 0 right up to n. So if you go from 0 to 0, what you get is just 1. And on the right-hand side, you'll get 2 to the 0 plus 1 minus 1, and this is true. Yeah. Okay. Second, if n is such that, and this is my induction hypothesis, 1 plus 2, blah, 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 right up to 2 to the n is equal to 2 to the n plus 1 minus 1. Prove P of n plus 1. So what is P of n plus 1? It is the sum of all powers of 2 from 0 right up to the power n plus 1. This should be equal to the next power of 2, 2 to the n plus 2, all this minus 1. So this is what I need to prove. Okay, using this horribly written induction hypothesis. This is better. Okay, so if if you're actively following me here, trying to do the next move by yourself, which is really the way you should be doing this, you will maybe see, okay, I've got the sum from 1 right up to 2 to the power n plus 1. So in particular, I have the sum from 1 right up to 2 power n in there. So I can apply my induction hypothesis to that. Yes, that's a winner move. Okay, so 1 plus 2 plus, we have to go through 2 power n. That's the left-hand side here. I apply my induction hypothesis right here. And it says that this is 2 to the n plus 1 minus 1. And I've got the 2 to the power n plus 1, which is still there. And yeah, like that. Okay. So I've just replaced the first part of the long sum by its value using the induction hypothesis. And so what I want to get is 2 to the power n plus 2 minus 1, but maybe you see how this goes. You see this is 2 times 2 to the power n plus 1 minus 1. And that's precisely the magic of powers of 2. 2 to the power n plus 2 minus 1. And that's it. Actually, this is one of the simpler ones. It's very similar to the very first one I did. So I have no messing around with inequalities or anything like that. So, okay. So far, so good. I got one last example, which is important for a slightly little different reason. We'll see in just a sec. I'm going to take a fresh new page for this, or maybe not. I've got, don't want to waste paper. It's ingrained. It's really, yeah. Okay, here's my example. Example 6. By the way, these are not numbered as in the book. I'm sure I'm just jumping here and there, doing it in the order I feel is more natural. Okay, conjecture a formula for the sum of the first I don't want to use, no, wait, for the first of the sum of consecutive odd integers. And prove it. Which means you have to make a correct conjecture, otherwise you won't be able to prove it. Or you can make a wrong conjecture and give a wrong proof for your wrong conjecture. But, okay. So what does this mean? It's not really well formulated, but let's just illustrate it. Okay, 1 plus 3, 1 plus 3 plus 5, 1 plus 3 plus 5 plus 7, 1 plus 3 plus 5 plus 7 plus 9. Let's see, what are these? This is equal to 1. This is equal to 4. This is equal to 9. This is equal to 16. This is equal to 25. If you can't guess what's going on yet, I'm not proud of you. Let's add another one. Let's add 11, 36. Okay. If you had never seen this before, you might be going, whoa, never seen this before. Because it's kind of simple and cool and unexpected if you've never seen it before. Okay, so if you add all the odd integers starting at 1 up to a certain point, what you get are the squares. Okay, so wow, that's cool, eh? It's very exciting. Yeah, so what's our conjecture? Our conjecture is precisely what I just said. The sum of the first n integers, odd, damn, is n squared. That's our conjecture. Okay. Right, so here you have the first 4, you get 16, the first 5, you get 25, and so on. Okay, so I want to prove this. Okay. There is, I believe, but I didn't have time to look it up, or I didn't want to think about it, I guess, but there's this, I think there's a short geometric proof of this, but let's prove it by induction. So proof by induction. Now here comes the tricky part. The tricky part for the youngins is to write this up properly. So what is the sum of the first n odd integers? How do you write that? Okay, so let's see. Let's just look at this thing, and I'm going to write below 1, 2, 3, 4. So how are these related? It's the last one. If you look at 7, it's 2 times 4 minus 1, right? And 5 is 2 times 3 minus 1. And 3 is 2 times 2 minus 1. Okay, so that's the pattern. Now, there are other ways of writing this. That's the simplest one, okay? So you remember odd integers are all those of the form 2k plus 1, but here it's more convenient to write them as 2k minus 1, just for the, but if you used the sum right up to the 2n plus 1, then the sum would be equal to, I guess, n minus 1 squared, something like that. It's just less convenient, but it is going to work anyway. But the pattern is this. This is 1 is 2 times 1 minus 1. 3 is 2 times 2 minus 1. 4 is 2 times, not 4, 5 is 2 times 3 minus 1. And 7 is 2 times 4 minus 1, etc. Okay, so that's the pattern I need to see. And so what I want to show is this. So P of n is the following statement. I take the sum of all odd integers, the n first odd integers, the last one will be 2n minus 1, like this. And I want to show that this is n squared. Prove P of n is true for all n greater or equal to 1. Okay, so I wrote it this way. There are other ways of writing it. You might have the sum right up to 2n plus 1, and then you start at n equals to 0, for example. But okay, so this is what I want to do. So let's see, induction. So what is P of 1? 1 equals to 1 squared. 2. If n is such that, I mean, by the way, the hard part was what I just did, is to actually write it down properly, but that takes a little practice, okay? But the proof by induction is just now, if that got you slightly confused, what I just did, just erase it from your mind and just look at the statement, how I wrote it here, and then it becomes an example just like the previous ones, okay? So if n is such that P of n is true, right? So that's our induction hypothesis. 1 plus 3, blah, 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 right up to 2n minus 1, all odd. This is n squared. Then prove P of n plus 1 is true. What is P of n plus 1? This is the sum of the first n plus 1. I'm almost done. N plus 1 odd integers. So this is 1 plus 3 plus 2 n plus 1 minus 1 equals n plus 1 squared. This is what I need to prove. Okay. Hopefully that's okay. Yeah. Stay with me. We're going to land this plane. Okay, so let's see. So if now I take a look at the left-hand side, I've got the sum of the first n plus 1 odd integers. So in particular, I've got the sum of the first n odd integers. Right, I've got these guys here. So now I can apply my induction hypothesis. So this is n squared, this part. And I have the rest of it 2 times n plus 1 minus 1. Okay, So what is this? So now there's no inequality, so it's very safe, right? You just have to mess around with this thing until you get what you want. You don't have to make any sort of guesses. So this is n squared plus 2n plus 2 minus 1, which is n squared plus 2n plus 1, which is n plus 1 squared. Hopefully that's okay.
Yep, that's fine.
So I am done for today, right on time, 15:15. Next time I will finish section 5.1. I've got a few more examples to do, but they're a bit more tricky. I mean, it's just induction again, but the when we use the induction hypothesis to go to P of n plus 1, we have to work a lot harder. And on Thursday, I'll do some review for the test. I'm doing problems before the test. Okay. Just to make sure the exam is on 4-1, 4-2, 4-3, 4-4. Yeah, 4-2, I'm not sure. I think I sort of covered that on the first test. That's the bases. So I don't think really it's not. So it's 4-1, 4-3, but I will send out a MEO with the precise contents soon. Okay, all right. See ya.
Thank you. Have a nice day.
Bye.
Have a great
Thank you.
day.
Thank
Goodbye.
Have a nice day.